Time to start. It's I guess many people were delayed by the end of the strike, so but let us start now. So I'm very pleased to introduce Pierre Kumar. Let me say a few words. He did most of his career in Urbana-Champaign, and is now professor in Texas A&M. So in the first place, he's, as all of you know, an oceanic scientist with a key contribution in all fields you can think of at the interface of mathematics and communication. He has well-known contributions, particularly in information theory, in stochastic networks, in stochastic control. It would be very long to list all the fields where he has seminal contributions. He's particularly well known, as you all know quite well, for his scaling laws, which is a new branch for mobile network, which is a completely new branch of information theory, and is really a major impact in this field, particularly. In addition to that, he has a very strong and marvelous sense of service. He's an advisor of many institutions throughout the world, not only in the US, but also in China, in Tsinghua, if I remember well, and many other institutions. I'm very glad he accepted also to help us for the design of the links. And I will stop here and give the floor to Pierre Kumar.
So thank you. Does this work? Yes. Okay. So thank you very much for inviting me here. It's a great honor and a pleasure. And actually, it's a fantastic opportunity. Every floor you have possibilities of interaction. So it's a great environment. Okay, so today I'm going to give you a little bit of a ride on the wild side. So this all started, we got a big contract, people in the US may know, it's called a MURI, on security of wireless networks. And usually when I get contracts, I don't pay any attention to them. I just do what I want to do. But this time I said, okay, let's try to look at this field of security. And supposing we had to develop a theory for it, how would we do it? So that's what it is. And the person, of course, who's done all the work is my last student at Illinois. He'll be graduating next month, Jonathan Ponaya. And there's also my colleague, Yi-Chan Hu. Okay, so the focus is on ad hoc multi-hop wireless networks. So just to set the context, what are they? Packets hop from node to their destination. So if you want to go from here to here, you take 1 hop, 2 hop, 3 hop, 4 hop, etc. So it's multi-hop. Okay. They don't require any pre-existing infrastructure. So after Hurricane Katrina, there actually were people who went and set up an ad hoc network. No centralized controller. And so all the decisions about operating the network, about configuring everything, has to be done in a distributed way by the nodes themselves. So there's a lot of distributed decision making. The nodes have to determine the power levels at which they transmit packets, what time to send a packet, what routes to use, how to cooperatively schedule the network, and so on. All these decisions have to be made by the nodes themselves. And in order to do this, you require a lot of protocols: medium access protocol, routing, transport, power control, many protocols. In fact, you need a complete protocol suite. Okay? All right, so that's the context. Now, the usual approach in many fields, and definitely in the case of wireless networks, has been to first design the system, write protocols which give you good performance. So you first develop protocols for good performance, algorithms and protocols. And then subsequently, what happens is that some attack is identified. Some people discover some vulnerability in the protocol, and then somebody develops a patch, a defense for that. Usually it's the same person in the same paper. Okay? But there's an attack, then there's a defense. And then somebody identifies some other attack, and then some other defense. And that is the way this field has evolved. And this is not just fiction, this is in fact exactly what's happened in this field. Several attacks, several protocols, etc. Okay? All right, what's the result? The result is a sequence of patches, okay, and an arms race. And the difficulty is that at no stage do you know what other attacks are possible in the future. You're always shutting the barn door after the horse has left. So you're patching the past known vulnerabilities. And the net effect is that there are absolutely no guarantees of security. Nothing. So this is the state of the field. Okay? All right. So what is the problem of defending against attacks? Now, so I'm going to give you a very theoretical view of this whole thing. Okay? My idea was just to shake up things. So let's see. So now, given a particular protocol, we can harden it against a particular attack. Okay? And that protocol is then immune to that attack. But the question that I want to ask is, can I develop some protocol suite that is immune to all attacks? Everything. Of course, it has to be within some context, right? Some model. We can't even list all the attacks. So how can you develop defenses attack by attack? So this approach is not going to work. So what can we do? Okay? So we need a system theoretic approach. Okay? And the way I'm going to view it is every attack is a policy in a given model of the system. What is a policy? A policy is if you see this state, or you have these observations, or you have this set of inferences, then do something, right? It's a lookup table. You see this, do this, see this, do this. That's what a policy is, right? A mapping from states or knowledge to actions. So every attack is a policy in some model of the system, okay? So the goal is to develop a model-based defense, okay? Now, so I'm going to assume some model of capabilities for the attacker, and I'm going to defend against all capabilities within this model. Now, there's another word for it. You can also call this Byzantine behavior, okay? So the nodes are allowed to do whatever they want to do within some model, okay? Now, the situation is this. So we have a whole bunch of nodes, some good, some bad. And the bad nodes can do whatever they want. They can indulge in Byzantine behavior. The good nodes have to do two things. They have to publish a protocol suite and then follow it. Why do they have to publish it? Because that's what the rules of the game, right? Okay, so now what we have is a game between protocols and Byzantine behavior. Okay, so the good guys are publishing protocols and following it. The bad guys are doing whatever they want to do within the model context. So question is, what is a model of the system for which we can actually carry out such a program of study? Okay, can we develop a theory and develop a complete suite of protocols? Is this possible? Okay. Okay, then the question is, but this is just security, okay? What about performance? Okay, well, so there may be many, many protocols that can defend against a bunch of attacks. How do we choose among them? Now, for people in network theory, they talk of throughput optimality. If you can get the maximal throughput feasible, that's called throughput optimality. But throughput optimality is not really optimality because it doesn't say anything about delay, right? So you can get to a finer sense of performance by talking of delay. Same thing here, right? If you just want to be secure, of course, easiest way to be secure is to lock yourself up in a room and don't talk to anybody, and you're completely secure, but zero performance. So the question is, how can we get performance? So what I'm going to do is I'm going to postulate a utility function, okay? And in my case, the utility function will be a function of the throughputs, okay, for various source destination pairs, for the good source destination pairs. And now we're going to get a zero-sum game. So there's a utility here. The good guys, who are always going to be in green, by the way, the good guys are going to announce a set of protocols and follow them. And they're trying to maximize this utility. The bad guys can indulge in whatever Byzantine behavior they want. Okay? It's very important that first you publish the protocols, then they're attacked. So this is max min of the utility. Okay? just as a small technical point, max-min is always smaller than min-max. Min-max is if the bad guys first announce what they're going to do, then you can do better, okay? So max-min is better than min-max. So we get a zero-sum game. So question is, can we develop an entire protocol suite which is max-min optimal, okay? And then there are some other issues that I'm just going to suggest, and they're worth thinking about. It turns out that it's like Meyerson's theory in economics of incentive compatibility, right? There are interesting problems related to choosing utility functions. You can even design utility functions which are hard to attack, and some which are easier to attack. And I'll give you an example. Okay, and there are so even it's like a little bit of a Stackelberg context. Okay, if you know what I mean. So there are some interesting issues on choice utility function. Okay, so the goal here is to develop a system theoretic, principled, and holistic approach where security is addressed first, not as an afterthought. That's the first thing we'll address. Performance is addressed second, okay, deliberately, okay. So, but I'm going to optimize it while preserving security. So I'm going to do a lot of, subsequently you can do a lot of optimizations, but security is guaranteed. Exactly the opposite of the reverse, of the usual approach, yes.
In your utility setting, so the utility and the X variable were referring to security or to performance? Performance. Given that the security...
Right. Yes. But the thing is that you can just think of performance as subsuming security also, because if I'm getting a good utility, then I'm okay. Okay. So that is the reverse of the usual approach. So the security objective is so it's going to be a clean slate approach. Okay. Yeah.
So you just said if I'm getting good performance, then security is okay, and I think that presupposes that the attacks are against, they're basically denial of service. Is that right?
Exactly like that, yes.
So that's the scope of security that you want.
That's the scope of security. So I'm going to explain that. So I'm going to use cryptography, and so I'm not talking of, So I will mention that. Okay, so we're developing a clean slate approach, which means nobody is going to use this, but that's okay. But it's provable, okay? And it's guaranteed if the model assumptions are satisfied. Now, the important point is this. The model can be attacked. And I'm going to suggest to you how we can attack the model. But I think that's a far better place to be in. Instead of defending attack by attack, it's far better to defend model by model. Okay, so you find some issues with the model, suggest let's do something, come up with a better model, okay? All right, so we at least elevate the game. And we'll develop a complete suite. Now, how do you view this whole business? You can view it in one of several ways. One is you could think of this as an existence theorem. That is, this is what is it that we can do, what is feasible. So it's just telling you some possibilities. Okay. Or if you're a little bit more optimistic, it is a suggestive. I'm going to suggest a different organization of things. A suggestive of how protocol suites should be developed, okay? And of course, as I said, we get max-min optimality. Max is over protocol, and min is over all actions of malicious nodes. Okay, clearly, a lot of explanation is needed, okay? Okay, so the basic objective is a suite of protocols that takes you from startup. What is startup? Startup is there's this primordial birth of the universe. A bunch of nodes are born. Okay, that's the startup, and we know, let us say, an upper bound on the number of nodes. Okay, now some of these nodes are good. Those are the green guys, and some of them are bad. Those are the red guys. And the good guys don't know who the bad guys are, and the bad guys know everything. So that's the primordial birth of a bunch of nodes. So I want to start from there. Okay, all the way and end up with a network which is a functional network carrying flows and optimizing utility reliably. Okay, a reliable network, yes.
What is the assumption of the mobility of the node?
Okay, I'll explain that in the model. Okay, so we're going to do static. Okay, that's one of the holes which I've mentioned. So basically, I want to go from big bang to a completely operational network. Okay, so we're doing the entire lifetime of network formation, because these are networks that are supposed to be set up without any pre-existing infrastructure. Okay, question is, what can go wrong with a network formed in the presence of bad nodes? Okay, so some nodes are bad. What could they do? Well, a lot of things. They could refrain from relaying a packet. You send them a packet, they don't relay it. They could advertise a wrong hop count. Okay, basically try to mess up your notion, your view of the logical topology. They could, here's something else they could just take their transmit power and just emit noise, white noise. Okay, they could just jam. Okay, they could cause packet collisions. They could talk when they're not supposed to talk. Okay, generally behave uncooperatively vis-a-vis medium access. You know, the thing about wireless medium is that it's a shared medium, so we all get benefits when we cooperate, but they could refuse to cooperate. They could disrupt all attempts at cooperative scheduling. They can drop an ACK. You send a packet, they don't ACK back. They can refuse to acknowledge a neighbor's handshake and behave inconsistently, sometimes good, sometimes bad, etc. And all of this is what is called Byzantine behavior. Okay. Now, what are the main results? Okay, so I've told you a lot of generalities here, the approach, and let me skip the actual protocol for the moment and tell you the final result. Okay. All right. So, bunch of theorems. The first theorem is I'm going to give you a complete protocol suite that will yield a network that is max min optimal with respect to this utility function, all the way from startup to optimized network. So that's what I'm going to attain. Actually, I'm going to do much better than that. I'm going to actually attain min max. Okay. So this, so in fact, I'm going to show you that there's a saddle point. And the min is over all behaviors of the bad nodes, and the max is over protocols. I'm going to get min max. In fact, I'm going to get even better. I'm going to show that I'm going to design a protocol suite where the bad nodes essentially, they're not going to benefit by doing anything other than two possibilities. One, either jam. Jam means just take your power and just send noise, and nobody can prevent a node from jamming. Okay. And or cooperate. So be good. Okay, be good or jam. That's it. Nothing else will give them any greater benefit to the bad guys. Okay. All right, and clearly you can never stop somebody from jamming, and you cannot stop them from cooperating. I mean, you don't know who the bad guys are, so if they're cooperating, they're good. Okay, so that's it. Okay. So the bottom line is that, and that's what the bad nodes are restricted to. When I say restricted to, I mean this in the incentive compatibility sense, in the sense that they don't get anything, they cannot do any better than this. Okay, and everything else, when I say ruled out, it doesn't buy them anything. Okay, so lying, dropping acts, all that doesn't help. Yes.
What about tampering the routing tables or something like that?
All that won't help.
It won't help.
Won't help. Won't help.
That's all subsumed under your topology manipulation.
Yes, yes, that's accounted for.
Do you consider the collusion of
Huh?
the bad guys? The collusion of the bad guys.
Yeah, bad guys can cooperate perfectly, omnisciently. They have perfect cooperation.
What is the noise that they have on the system?
Exactly. So I'll get to the model. So I've told you the philosophy and then the result. Now let me explain about the model. Yes.
Max optimality is relative to a particular utility.
Exactly.
So suppose
yeah.
a malicious node has an unknown utility function. So for instance, maybe my goal is not to disrupt everything, so I wouldn't jam. But maybe I want to prevent Daniel from successfully communicating. So whenever he sends something, I'll jam. This is not quite jamming. Right? It's not cooperating either. In what way?
Okay. So what you're talking about is non-zero sum games. You have some objective, they have some objectives, and they're not the same. And then people talk of Nash equilibrium and so on. Now what I'm doing here is I'm viewing it from the viewpoint of the good guys. Okay. Everybody who's not good could potentially be hostile, but they may not be. What is the worst that they could do? Okay, that's what I'm showing you. Now, of course, if they're not as bad as that, then you can do even better. Okay, but this is what I'll guarantee. Okay, one question that first comes up is, why on earth would a bad node ever cooperate? Why should it cooperate? Well, it depends on the utility function. Okay, but I'm allowing all utility functions of throughput. There may be some mild restrictions on smoothness and so on, but basically all functions. For example, take this utility function, which is the minimum throughput you give to a set of flows. So this is like maximum fairness, right? So you're judged by how rich the poorest person is. That's this utility function, okay? Socialist objective. Okay, now let us say I have that, and let's suppose there are 3 nodes in this universe. A and B are the good guys, C is a bad guy, okay? And the throughput from A to B is XAB, the throughput from C to B is XCB, okay? Now, let us suppose that C is far away. It's far away from AB. Now, if C is far away, he's got limited power. If he jams, he's going to create very little noise here. So he's going to hurt the signal to noise ratio very little. So he'll detract from this throughput XAB very little. In fact, if he's infinitely far away, then he doesn't hurt this guy's throughput at all. These guys will get exactly as much throughput as the maximum feasible because he's so far away. Okay? On the other hand, if he's transmitting a signal, the signal also is received with a very low power here. So the data rate that you get is low. Data rate depends on the signal strength, right? SINR. If that's low, you get a low data rate. So low signal and low interference at B. Now suppose he jams. Then as I mentioned, he can only reduce this throughput very little. In the limit, if he's very far away, if the distance between B and C is infinity, so C is extremely far away, then he doesn't really hurt you at all. These guys get their maximum throughput. On the other hand, supposing he says, I'm a good guy, so count me in, okay? Now he's a good guy, but very hard to please, because his signal strength is so low that in order to give him a throughput equal to this guy, you'll have to spend all your air time just catering to him, because the utility function is maximum fairness. So under this utility function, if he pretends to be good and says, I'm very far away, then he gets throughput 0. These guys get 0 throughput. So he actually hurts the system more by cooperating and being hard to please than by jamming under this utility function. On the other hand, supposing you didn't take this utility function, you set the sum of the throughputs. Then that cannot be attacked by this guy, right? So there's a very interesting meta game, if you will. How would you choose your utility function in a hostile environment and design protocols around that? Okay? All right. Okay, now let me tell you a little bit about the ingredients in our approach, okay? And you should think of all of this as an initial foray, okay? And the idea is, let us see what more we can do, okay? So I'm going to assume all the standard cryptography stuff. Immediately that takes it out of the domain of information theory, because information theorists don't believe in cryptography, okay? So I'm going to assume everything. All packets are encrypted, signed, etc., everything. So the bad nodes cannot create fake packets. They cannot alter good packets without getting caught, everything, okay? Another ingredient of our approach will be clocks and synchronization. Now you say, why do clocks and synchronization come in? And the reason is the following. Without a notion of time, we cannot talk of throughput, because throughput is bits divided by time. If you don't agree on time, we don't know the throughputs, how can we optimize? Okay? So we need a notion of time, okay? Because without throughput, we cannot talk of utility the way I'm defining utility. So time is an essential ingredient. Okay, no, you cannot escape that. Now, what about common time, synchronization? Well, you could try to get away from that, but what I'm going to do is I find it much easier to design this protocol suite that's secure by first fixing the clocks and then doing things, because I'm going to be able to cooperate in a much easier way. So this is not absolutely essential. Perhaps you can do a completely event-based system, okay? But this is just the first shot, so I'm going to show you that I can do it this way. Okay, so with the notion of common time, nodes can cooperate temporally and share resources in a time-based way, and for me that's easier. Okay, so cooperative scheduling will be possible. So synchronization will be a fundamental ingredient in my approach. But clocks have to be there in all approaches. Okay, so now we come to the model, and this is where you should criticize. Okay, I'm going to assume a bounded domain. The only reason is I don't want things to be so far away that limits and so on. There are n nodes, so n is known. Okay, some bad, and I'll also assume now there are the models at various levels, and I can work with all of them. One model is a more physical model where you tell me how much power is in your transmitter, you tell me how much noise, and then I can work with a Shannon theoretic approach and try to talk of rates and so on. So that would be a very physical model of the communication system. Or you could just say forget that physical thing. I'll just assume there's a bunch of modulation schemes at different rates. There's a low rate modulation scheme that's pretty robust to jamming. There's a high rate modulation scheme that gets affected by jamming. So you could directly work with modulation schemes and rates. In fact, just for simplicity, let's assume that. Okay? Though I can work with a more physical model also. Yeah.
You assume n is known.
Upper bound and n is known, yes.
But then how do you take care of the jamming nodes which just pop up without...
Okay, so that's a good question. So there's two, I'll get to that, but let me just say it very briefly here. There are two models of the formation of the universe. One is a Big Bang approach, all the nodes show up simultaneously or within a bounded time of each other, or another model of the universe where nodes keep showing up and there's unbounded thing. That's much more difficult, but we worked out the theory for that. I'm not even going to talk about that today. But in this particular case, let's suppose they're all bound within a bounded time of each other. Big no. I don't know. I'm going to assume that nodes are not mobile. So this is immediately something that you should say, wait, this needs to be improved. Perhaps it can be. Perhaps if the mobility is slow, I can develop a quasi-static theory. So things will begin to equilibrate before nodes move. If nodes are hypermobile, this approach won't work, okay? But I have not done it for the quasi-static case either. I'm going to do strictly for the static case, okay? And as I said, let's just assume there's a finite set of modulation schemes, or you can have a more physical view of the universe. Okay, continuing on the assumption. What am I trying to do here? Okay, so I'm big on philosophy, low on facts right now. I'm trying to give you a model of everything, the Gestalt, everything. That's my model. It's not just the security part or the wireless part. It's everything. And I'm developing a complete protocol suite under that complete model. Of course, it could be extended, criticized, etc. But that's the kind of debate I want us to engage in rather than attack by attack patches. Okay? Okay, I'm going to make some connectedness assumptions, which for people, I noticed that there are some people working on Byzantine protocols yesterday. Okay, so suppose that I'm trying to talk to somebody and all the rest of the world is jamming. So assume that everybody else is hostile and jamming, and I'm trying to talk to somebody. Suppose there's a modulation scheme, a low rate modulation scheme at which I can still talk to that person. Then I'll say that there's an edge. This is just an abstract, I can make use of edges which are not so worst case, but I want to define a certain connectedness property assumption. So let us say that there's an edge between two nodes ij, when they can communicate at the lowest rate modulation scheme when everybody else is hostile and jamming. Okay? I'm going to assume that then the resulting graph is connected. Okay, so there's a worst case connectedness assumption. In fact, I'm going to assume that the subgraph of good nodes is connected. This, by the way, makes a lot of the Byzantine stuff go away. It makes it easier. Okay. Actually, I don't need this, because if they're not, then I can develop this theory in islands of connectivity. But it is much simpler this way. So let's just do it that way. Yeah.
So this is static in terms of the
Completely
location of nodes, but
yes.
there might be some, nevertheless, fading that depends on time. And this
No, I'm not. I don't have probability theory, as you'll see in a second. Okay, so that's another whole. Okay, so I said low rate modulation scheme. So I'm assuming some handshake that gives you a reliable rate. Okay, so I've abstracted away the unreliability to a higher level. Okay. Which raises interesting questions also, by the way. So every time you get a packet, every time you send me a packet, I can say, oh, gee, there was fading. You know, how do you defend against that? I'm not addressing that here. Okay, I'm also going to assume clocks. I'll assume that every node has a clock, and that clock ticks linearly with respect to Greenwich Mean Time. Okay, so every node has a linear clock. Now, ideally, the slope should be 1, but they're not. Okay, so I'm going to call that slope as a skew, and there's an offset. Okay, okay. I'm going to assume that all skews are bounded. That is, no two clocks are more than 10 times as fast as each other or something. Okay, so all skews are bounded below and above.
Do you think that this is feasible with Byzantine nodes, unless you have a global tick?
No, I'm just going to assume that you have a device called a watch, which is twice as fast as Greenwich Mean Time.
This is provided before.
Before everything, yes. So there is a, yeah. But I'm going to say one more thing. I'm going to make it digital in a second, which makes it more difficult. So I'm going to assume that there's an affine clock. Okay, actually, a little weaker assumption. I'm going to assume that the clock is digital. Okay, this actually makes things more difficult for me, because in between two ticks, I don't know the time. Okay, and that actually introduces a lot of problems, because when I'm trying to do estimation of certain things, right, this imprecision has to be taken care of. Okay, I'm going to make things even more difficult by assuming that clocks do wrap around. This actually is a huge problem, even when you have cryptography, and the reason is the following: because you're open to replay attacks. So I can record your packet that you sent, which was signed with a certain time. I can't read it, I don't know. But if I replay it at a later time, then it looks just like it came from him if the clocks have wrapped around, right? So under wraparound, there's a replay attack possible. Okay, I'll allow that. Okay, and system startup. As I mentioned, I'm going to assume this primordial Big Bang. All nodes are bound within a bounded time of each other. And we can relax that, but I'm not going to talk about that. Okay. I'm going to assume also that packets experience a delay in going from I to j. And they incur a delay in going from j to I. And these two delays are not necessarily the same. Now you can say, why is dij not equal to dji? Because this delay is not just electromagnetic propagation delay. It is the delay of time stamping, operating system interrupt, going through the protocol stack, MAC, etc. Then you get to the tip of the antenna. Okay, and then you get the electromagnetic thing, and then at the other end the packet has to be decoded and the timestamp has to be read out. So I'm taking that delay, and depending on the load on the operating systems and so on, this heterogeneous thing, these delays generally are different. Now, of course, you could assume they're equal, but if that's not real, at this granularity, they're not. Okay, this delay dominates the electromagnetic propagation delay. Okay, all the cryptographic stuff I'm going to assume. And a network utility function over conforming pairs. Okay, I need to take one small digression here. And to say something about clocks, and then we'll come back to this.
There was
Yeah.
a maximum fairness in addition.
No, no, no. That's just an example of a utility function. But I'll allow more general utility functions. So you could take a utility function which is the sum of the squares of the throughputs, or the sum of the throughputs, or whatever. But Max-Min is also possible. But under Max-Min, there are certain, yeah. So what you get will depend on the utility function you choose, which makes it a meta issue.
Right, but
Yeah.
I think you want that.
Here I'm doing summation. Yeah, yeah.
So it's just simple stuff.
I could do that also, but just for concreteness, I'm doing summation here.
What are the pairs that you refer to?
Conforming pairs. All the people who are not detectable as not conforming to the protocol. Okay, you'll see that.
Would include bad nodes who are behaving correctly.
Correct.
to generate
Correct.
utility and take
Exactly. Yes.
You assume all, at least good nodes are,
Good.
have similar capability?
I'm assuming good nodes. All nodes. I've given you the model for all nodes. Okay. I've given you the model for all the good nodes. Okay. The bad nodes can omnisciently further conspire and do things. Yeah. Okay. So clocks, just a small digression here. Okay. No two clocks agree, and there are issues. How can you synchronize clocks in wireless networks? And the reason why I'm synchronizing clocks is because it helps me with respect to the security problem. But there's another chicken and egg problem. What about the security of clock synchronization itself? How can you attack that? Everything is attackable, okay? All right. So first I want to tell you that it's impossible to synchronize two clocks. Impossible, okay? So let's assume there's a clock 1, clock 2. And as I said, they take delays D12, D21. Packets take to go from there to there. And this is the clock on node 2, clock on node 1, and there's a linear characteristic, and there's a skew, and there's an offset. So this entire problem is described by 4 parameters: D12, D21, skew, and offset, right? 4 parameters. What I'm going to tell you is that it is impossible through any sequence of timestamp packet exchanges to determine these 4 parameters. Impossible, okay? And the proof of that is actually quite trivial, okay? So let us say that this is clock 1's timeline, clock 2's timeline. Let us say that clock 1 sends a packet, and he sends it at local time S1, which he timestamps into the packet, okay? And let us say it is received at remote time R1. Now, the delay incurred is D12 in local time units, right? Now, what is the equation for R1? R1 is related to, it's the sending time plus the delay transformed to the new coordinates, right? So there's a certain equation between receive time and send time, okay? If you send a packet backwards, there is another equation, a red equation, okay, between send times and receive times. And you can keep sending packets all day long, and you keep generating blue equations and red equations, okay? And then they can exchange timestamps in future packets and so on. So they know. So you get this set of equations, and the nodes know all these timestamps, and what they want to determine is these 4 parameters. Now this is a nonlinear one-to-one onto parameterization, but essentially there are 4 parameters here. And this is, so you know this matrix, you need to figure out this. So you need to solve a bunch of linear equations. However, if you look at this matrix here, it's rank 3. If you subtract this column from this, you get this. So there's no way from a rank 3 matrix to determine 4 parameters. So it's impossible, okay? All right. So what is determinable? Because I need to work with exactly what is determinable, okay? It turns out you can determine the skew. That's pretty easy, right? If I send you 2 packets 100 seconds apart and you get them 110 seconds apart, then your clock is 1.1 times my clock. So that's easy, okay? Round trip delay, that's also easy. I can send you a packet and you can send it back to me immediately. That's round trip delay, that's doable. Here is something that is a very interesting capability, very interesting. It turns out I can never know the clock time on your clock. However, I can always do the following. I can send a packet to you and say you will get it at 3 o'clock by your watch. And you will, even though I don't know when 3 o'clock is. So I can predict the time at which you will get a packet, okay? So I can conspire to send a packet at a certain time, which will arrive to you at a certain time, according to your clock. What is unknown? Offset is unknown. In fact, here's a simple way to think about it. Supposing I send you a packet at 1 o'clock, and you get it at 2 o'clock. There are two possibilities. Our clocks are completely synchronized. It took 1 hour to go from me to you. So delay is 1 hour. Or there was zero delay, but your clock was offset by 1 hour. And you can never separate delay and offset. Impossible. Okay? So that's unknown. So basically the delay is an affine function of the unknown offset. Okay? And I'm going to skip some other details. And all of this is just done by staring at the null space of this matrix. Okay, but the capabilities that I'm going to work with are three things. Skews. Nodes can determine each other's skews. They can determine round-trip delays, and they can send packets to each other at certain times. And all of this is good in guaranteeing certain properties and things, like detecting when bad nodes are falling up and so on. Okay, now a little bit about the scheme. Very little, because this is like a 100-page thing. The protocol suite. But how much time do I have?
Like 10 more minutes? Or?
Okay, that's fine. Okay, so the phases of the protocol suite. So this is the Big Bang. They're born. And then, so when the nodes are born, they're all blind, right? They don't know who's their neighbor. They know nothing. They're just born blind. So there's a time period in which they figure out who their neighbors are. Okay? There are very interesting questions here. When we're all blind and some of us are hostile, how do we determine who each other's neighbors are, especially when the medium is shared? So we'll get to that. Then, after figuring out a little bit about the neighborhood, they try to obtain a view of the network. So this is like a link state view or something. So they try to patch together this local piece of information in some consistent way. That raises very interesting questions about Byzantine again there. They try to get a global view. Okay. Then after they get some kind of a global view, then they see, okay, given that this is the network, this is the way we should operate it to maximize the utility. So this is when you should send a packet, this is when you should relay, this is when you should send, etc. So we cooperatively schedule the combined network resources once we have a view of what's out there. And then we start sending data. So we've decided on the schedule, we start sending data. Unfortunately, the bad nodes could be behaving well until now. They've let you completely agree at something, and now they refuse to cooperate when it comes to the data phase. So we're going to have to verify who didn't do well, etc. And then we'll prune. Okay, we'll prune. And then actually we're going to keep pruning away until we get to the set of nodes which are either conforming or weeded out. Okay, that's what the thing is, etc. So we go through a bunch of loops, and then we terminate at a certain point, and I guarantee epsilon optimality of the utility function. Okay. Okay. So that's the overall scheme. Now let me show you some theoretical. I want to show you some theoretical challenges. Okay, and we've got a complete protocol suite for all of this. So actually, this is a confluence of several things. It's all of distributed systems stuff. It's got game theory things. It's got whatever, wireless. And hopefully the model is relevant to wireless and so on. Though I'll mention some open questions. You had a question?
So what the previous slide shows is that there is a way to determine who are the conforming nodes.
Correct. 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 Because I ask you to send a packet at 2 o'clock to him, and then I can get a signed agreement. Now, of course, there are some issues here. Okay, what are the challenges? Okay. The first challenge in neighbor discovery is when we are born, I need to find out who the neighbors are. But that requires a handshake, right? I need to send you something saying this is me, then you need to say, yeah, I heard you, this is me, back. So we need a two-way handshake, right? And now, it sounds like a trivial problem, but how can we guarantee that any two nodes can communicate to packets with each other, given that nodes are half duplex? And also you can have collisions. So there's primary conflicts and secondary conflicts. Collisions are secondary conflicts. Half duplex is primary, okay? So I cannot listen when I'm talking, so maybe you're talking to me at the time I'm talking to you, so neither of us hears each other, etc. And other nodes can cause collisions. It turns out, and they should operate with clocks which have different skews and so on. So we need a guaranteed orthogonal medium access scheme, which guarantees that any any pair of nodes can exchange a handshake within a bounded time. Okay, so a totally deterministic scheme, and the answer is yes. Okay, so we will develop. So such a scheme we have to develop. Okay, which works with different clocks and offsets and everything. Then after they get a handshake, identity handshake, they'll need to synchronize clocks. Okay, so they'll need, and then you'll need to work with the fundamental limitations on clock synchronization. They can determine their skews, but not their offsets, and so on. Then after that, they form a network. Okay, they need to form a network, and we're going to piece together local informations, right? But we want to make sure they are consistent. Okay, so individual links may look okay, but when you look at it overall, there could be global inconsistencies. So for example, let us say he says his clock is the same speed as mine, and she says the clock is the same speed as him. So ultimately, I conclude that that person's clock is the same speed as mine when I go through this path. But when I go through this path, this person says I'm twice as fast as you, I'm also 3 times as fast as you. So I can get inconsistency over different paths, right? Because nodes can lie. Everything is under attack. So, and all of this has to be done in the presence of malicious nodes. It's possible to do all this. Yes?
Just a question about reporting information. Is there an assumption about link symmetries built in? I guess what I'm trying to understand is, let's say, Francois says, Francois is good. He says,
right.
Here's my band, here's my capacity gym.
Right. I'm assuming symmetry here.
You are. Okay.
Yeah. So that would come from.
You get the verifiability.
Correct.
So long.
Correct. I suppose you could do it even without asymmetry, but it will be much more complicated.
I don't see how you could do that, because I would be the only one who knows my local.
I know, but then I'll have to close it. I'll have to assume some strong connectivity or something. I mean, I'll have to work with a directed graph now. Okay. And then they draw up a schedule for transmissions and send data, but then some malicious nodes that conformed hitherto and remained hidden hitherto may decide to mess you up at that point. And this requires a check to detect malicious behavior and another round of network-wide computation, etc. Okay? All right. And then there are, as I mentioned, there are challenges caused by clock wraparound, which allows replay attacks. And all of this has to be done with a finite bound on clocks in the presence of skew errors because of these digital clocks. And then there are also more challenges, especially between these two things when you aim for epsilon optimality. Okay, so what is needed for each phase? Orthogonal MAC, there's a theorem, okay? There exists a way which MAC that allows any pair of nodes to exchange a message of a certain time within a bounded time. So there's a theorem. And then there is a synchronization protocol which allows them to determine skews and so on. Then they form a topological view, right? And they can, the nodes, we can get to a stage because of all the Byzantine assumptions, okay, lining up, that all the good nodes will decide on the same topological view. The common topological view after a bounded number of transmissions. I can guarantee that, in spite of attacks. But even though they may have a common view, it may be inconsistent internally. Okay, we may all agree on the same thing, but it could be wrong. Okay, so for example, as I said, when you take the product of skews along a path, that may be different from the product of skews along a different path. So now, and you cannot tell who's lying if you just have this information. So, but we can actually, we have a consistency check protocol that circulates a packet around so you can actually catch who's lying. There's the details there, okay? So we can actually determine that. And then there are some issues, the question is chicken and egg. Is coordination before synchronization or after synchronization network-wide? There's a way to handle that, okay? You have to give some slop between different phases so people can roughly agree, and there are some issues there. Okay, there exists a schedule that allows unsynchronized nodes to complete a finite number of protocol stages within a band, etc. And then there's some utility maximization over some rate region that is done. Okay, and then after that, then they go to the date of transfer phrase, and the verification also can be done within a bounded time, because people can need to just report the first packet that didn't show up as advertised, as required. Okay, so you can do pruning and so on. Okay, all right. Then ultimately, at the end of the day, you get this optimality. Okay, let me make some remarks. Okay. I remember once Wendell Fleming had come to visit me for a seminar many years ago, and then he talked about all this stuff, and he said, I have a dehydrated elephant. Okay, so that's where we are. Okay, all right. So how should we view this? Perhaps you can view this as an existence proof that you can actually do something. Okay, certain things are feasible, or perhaps as suggesting an architecture. Network discovery, neighborhood discovery, network discovery, synchronization, etc. If you want to proceed in a time-based way. But maybe you'll write another paper which says we can do it event-based. Wonderful. Okay. Basically, I'll be very happy if there's a follow-up paper which says it's all wrong. Here's a better way to do it. That's what the goal is. So hopefully, it will spawn alternative architectures for thinking about this whole thing from the ground up as a first-class citizen security, not second. Okay. There are very interesting questions that come up in design of utility functions. Okay. Lot of issues. A lot of these protocols take transient, so even though they're asymptotically optimal, the transient may be large. But we can optimize there. We can do all the optimizations that one does. You can do here, but now you're guaranteed security. So optimization post-security, not pre. Okay. So you can do, that's what I said. Extensions, okay. This business, I said bounded time, that we can handle. I can do that. There are many abstractions and assumptions that I made that can be attacked. Okay. Let me give you one. I'm assuming a perfect channel. So there's a low rate reliable modulation scheme. Okay, rate adaptation or something. But supposing you want to come down to a more probabilistic packet thing, actually a very interesting question. Now, if you introduce probability theory, I can only give you probabilistic guarantees. It requires a very, quite complicated theory, but I think it's still doable. Mobility. This gives rise to a time-varying system. The characteristics of system are changing with time. But if they're changing slowly enough, maybe a quasi-static approach is feasible. Information theory, security, I think this is hopeless. Okay, because information theorists don't believe in cryptography. All right, but maybe. Let's see. Anyway, so that's where we are, and thank you.
So we have time for a couple of questions.
So, as far as I understood, one of the ingredients of your proposal is the Lamport presenting general problems.
I'm sorry, I cannot hear you.
Presenting general problem of Lamport. So, I assume that you use the cryptographical version of the...
Right. So because I can sign, there is a bounded time, there's connectedness, this problem becomes simpler.
They have also the version where they do not use the cryptographical
Right.
tools.
So you can relax some assumptions, maybe. Yeah. But I think by and large these assumptions are satisfactory. The thing that I'm unhappy about is mobility, and then this probabilistic packet loss. Those are the two things. The time varying and the probability are the things that I think are major open issues. The rest of them are okay. Of course, you can fiddle around the edges and try to improve them, but by and large, they're okay, I think.
So you have the same bounds on the Byzantine node as the Lampert's bound?
Yeah, they're all doubly exponential something. The bounds are terrible. I don't care.
No, I mean the fraction of
No, I don't need that. So I don't need that fraction assumption at all. So I don't need that there should be, I don't even need that the majority of the nodes should be good. Even if there are only 2 good nodes and everybody else is bad, that's fine with me. Yeah, so I don't need that assumption. Yeah.
So you don't need that assumption because you can do verification afterwards. So if I lie, I kept thinking about this one bad node, one good node surrounded by lots of bad nodes, but of course there's got to be one other good node that's connected
Correct.
to you so that information leaks out.
Exactly.
So if I'm a good node, I'm surrounded by a bunch of bad nodes. They're all
Correct.
saying, oh, Jim is lying. Eventually, the fact that I'm lying would come out, right?
Correct.
Or, sorry. Eventually, the fact that all of the liars around me
Correct.
unjustly accusing me of lying,
Correct.
their badness would come out because
Correct.
you've got that verification.
That's right. That's right. So these assumptions all dovetail. So certain, I don't need to. I don't need the most general Byzantine generals thing. There are other things that help me out here. But as I said, the major ones are mobility and probability. If I knew how to do that, I'd be happy. Yeah. Yeah. Mobility may be easier than mobility and probability may still be feasible. Yeah. Sorry.
You suppose that good nodes fully cooperate, right?
I'm sorry.
You suppose that good nodes fully cooperate.
Fully cooperate. That's the definition of good.
Selfish behavior. Imagine I want to maximize my utility, but I don't maximize.
Then you're not good.
I'm not good.
No, because good means that you'll follow the published protocol, which is designed for a certain utility.
And could you push forward the settings towards
Yeah, I mean, you could try to make this into a non-zero sum game and do certain things. Yeah. I mean, maybe you can try to prove that things go to a Nash equilibrium or something. Yeah, that's possible.
It's sort of a philosophical question. So we all make assumptions in our models. You really dwelt a lot on clocks and skew and stuff like that. And as a networking person, I would have, if you had said, assume all clocks are synchronized, I'd say, okay, fine. But then you make assumptions about like symmetry between channels and stuff like that that a wireless person would jump all over you about. And so I'm just curious, why do you think that, did you focus on time so much because you think that that is sort of one of the supercritical things in coming up with a theory like that, or?
I think theoretically otherwise things would be a lot more complicated. I don't actually speaking need to assume complete symmetry of channels as long as it's there's an undirected graph, I'm okay. But I'm not saying the rates are the same and so on. So maybe I can talk to you at 10 bits per second and you can talk back to me only at 1 bit per second. But if there's a half bit per second modulation scheme at which both of us can talk, that's the kind of edge I'm looking for. So not symmetry, but a little bit less. Yeah. So connectedness, symmetry of connectedness or something like that. Yeah. Logical symmetry. Not rate symmetry. Yeah. So.
More questions? It's a break here. So
Yeah,
we have a coffee break now, and we resume at 11. And the coffee break is the same place as yesterday. So let's thank Kumar.